think you're going to be defensive in a fighter plane, you're lost.
It's one-to-one combat, and you got to be aggressive.
During World War II, military aviation made a decisive technological leap. Germany, the United Kingdom, the United States, Japan, and the Soviet Union pushed the development of air control, enabling the defense of entire territories, as seen in the Battle of Britain, and organizing night interception against Allied offensives. That convergence of range, altitude, and firepower turned the sky into the determining variable of the conflict. Several aircraft defined critical moments. The P-51 Mustang imposed its unmatched range by escorting bombers all the way to Berlin, crippling the Luftwaffe's operational capacity. The Supermarine Spitfire proved crucial in the Battle of Britain thanks to its rapid climb rate, essential for intercepting German fighters. The B-29 Flying Fortress demonstrated its greatest impact during the Schweinfurt-Regensburg raids, where its 13 machine guns turned each formation into an extremely dangerous target. This ranking brings together the most lethal models that decisively influenced the air battles of World War II. Which were the 15 aircraft that marked a before and after in aerial warfare? P-51 Mustang, the American escort fighter that crippled the Luftwaffe. In the summer of 1943, the daylight strategic bombing campaign over Germany entered a critical phase. B-17 Flying Fortress and B-24 Liberator formations, heavy bombers of the USAAF, the United States Army Air Forces, began suffering losses that could no longer be accepted as the cost of the mission. Beyond the range of the available escort fighters, every deep incursion into the Reich became a high-stakes gamble. In August, 60 bombers were shot down in a single mission. In October, on Black Thursday, another 60 fell over Schweinfurt. Allied fighters could not accompany the bombers to the deepest industrial targets, and the Luftwaffe exploited that gap to concentrate its interceptors. If the situation did not change, the air campaign was doomed to fail. The arrival of the Mustang was the result of a chain of technical decisions that had not originally aimed to create a long-range escort fighter. In 1940, at British request, North American Aviation developed a new fighter with a laminar flow wing and an efficient cooling system that reduced aerodynamic drag. The prototype demonstrated good range and speed, but its Allison engine limited performance at high altitude. The transformation came when British engineers experimentally installed a Rolls-Royce Merlin engine with a two-stage supercharger. The increase in power above 20,000 feet turned the Mustang into a competitive fighter against German models. North American and Packard adopted the modification and began producing the Merlin-powered P-51 in 1943. Equipped with disposable external tanks, the new model achieved more than 2,500 kilometers of range, enough to escort bombers from England to Berlin. In December of that same year, the first Mustang groups began deep penetration missions over German territory, immediately reducing the Luftwaffe's operational freedom. The turning point came in March 1944 when, for the first time, American bombers reached Berlin with escort from start to finish and returned with significantly lower losses. In that context, the Mustang began to clearly demonstrate its advantage over the Bf-109 and the FW-190, the latter a high-performance German single-engine fighter. Its combination of operational altitude, speed and range allowed it to dictate engagements on its own terms. Armed with 6.50 caliber Browning machine guns, the standard heavy armament of US fighters, the P-51 carried enough firepower to shoot down enemy interceptors and damage German bombers in brief, controlled and precise attacks. Doctrine evolved as well. General James Doolittle, commander of the United States 8th Air Force, ordered escort fighters to leave the bomber formations when necessary to seek out and destroy German interceptors. This directive turned the Mustang into an offensive tool. Pilots attacked groups of fighters before they could reach the bombers, and on the return trip, strafed airfields, workshops and parked aircraft. The Luftwaffe began losing veteran pilots at a rate it could not replace. By late 1944, the 8th Air Force was operating mostly Mustangs, and bomber losses dropped dramatically. With more than 5,000 confirmed kills, the P-51 became the most effective American fighter of the war. Its arrival made it possible to sustain the air offensive that crippled German production of synthetic fuels and aircraft, paving the way for the ground operations of 1944 and 1945. But the Mustang's dominance can only be understood in relation to the adversary it faced. For years, the most feared hunter in Europe was a German model that amassed more victories than any other in history, the Messerschmitt BF 109. Messerschmitt BF 109, the German fighter with the highest aerial victory count in history. In 1934, the Reichsluftfahrtministerium, the Air Ministry of the Third Reich, launched a competition to define Germany's future standard fighter. Arado, Heinkel, Focke-Wulf and Bayerische Flugzeugwerke all submitted proposals. There, engineer Willy Messerschmitt defended a very specific idea: to concentrate a powerful engine within the smallest possible airframe, minimizing drag and prioritizing speed. The result was an all-metal monoplane with an enclosed cockpit and retractable landing gear, perfectly aligned with the Luftwaffe's accelerated modernization. The BF 109 entered production in 1936, and by 1945, more than 33,000 units had been built, making it one of the most produced fighters in history. Its first combat campaign was the Spanish Civil War, beginning in 1937, where early variants demonstrated an advantage over the Soviet fighters used by the Republic and served as a testing ground to refine armament, engines and procedures. When World War II began, the BF 109E Emil was already the backbone of German fighter aviation, capable of exceeding 560 kilometers per hour and equipped with a mix of machine guns and cannons that made it effective against both fighters and bombers. In Poland, in September 1939, it carried out air superiority missions, escort duties, and attacks on airfields. In 1940, during the campaign in France and the Netherlands, its performance fit into a doctrine aimed at neutralizing the enemy's air force on the ground and then dominating the airspace to enable the ground advance. The Battle of Britain revealed operational limitations of the BF 109 that were difficult to overcome. Its short range barely allowed it to sustain combat over southern Britain, and the time available over the target was extremely limited before having to turn back. The RAF, by contrast, fought near its own bases, able to rotate pilots and aircraft quickly. In this context, the matchup became more balanced, especially against the Supermarine Spitfire, a high-performance British single-seat fighter. It was not clearly inferior in speed, and the real differences appeared in aspects such as climb rate, dive capability, or turning performance, always depending on altitude and the energy each pilot carried into the fight. After the autumn of 1940, the BF 109 remained central to the Luftwaffe, but it became clear that combat performance alone was not enough. Range and pilot availability also shaped the outcome. In 1941, Operation Barbarossa, the codename for Germany's invasion of the Soviet Union, opened an entirely different scenario. The vastness of the front, the high number of daily sorties, and the initial surprise effect during the first months translated into exceptionally high victory counts for German fighter pilots. In that environment, the reputations of several aces, pilots with numerous confirmed aerial victories, became firmly established. Names such as Erich Hartmann, Gerhard Barkhorn, and Günther Rahl became closely linked to Eastern Front units like Jagdgeschwader 52, a Luftwaffe fighter wing that operated almost continuously over Soviet territory. At the same time, the aircraft itself evolved. The BF 109F improved aerodynamics and handling. The BF 109G incorporated more powerful engines and reinforced armament, though with increased weight. By 1944, with deep Allied escort missions and constant pressure on airfields and fuel supplies, the BF 109 still appeared in the skies, but increasingly as a system dependent on resources Germany could no longer sustain. During that transition, the Luftwaffe needed a complement that not only fought, but reshaped the tactical balance in the West, and that role was assumed by another German design that burst abruptly over the Channel in 1941, the Focke-Wulf FW 190. The German fighter that dominated aerial combat, Focke-Wulf ULF 190. In the autumn of 1941, reports from British pilots over the Channel all pointed to the same conclusion. A new German fighter was outperforming the Spitfire EMC in speed, acceleration, and firepower. Very quickly, the evidence became operational. The FW-190, introduced by the Jagdgeschwader from bases in occupied Europe, imposed an immediate shift in the balance of power, not because of a single feature, but because of the combined effect of its engine, airframe, armament, and handling at medium and low altitude. The program had begun in 1937 as a response to a strategic German vulnerability, relying almost entirely on the Bf-109. Kurt Tank, the chief engineer, designed the FW-190 around a BMW radial engine, air-cooled, a choice that prioritized robustness and damage tolerance. After initial issues with temperature and reliability, the A1 variant entered service in 1941. In combat, the aircraft stood out for its high roll rate, strong acceleration, and responsive controls, allowing it to change direction rapidly, enter and exit engagements at will, and fire in short, decisive passes. Its armament, machine guns and 20mm cannons, increased lethality against fighters and especially against bombers. Pressure on the RAF became clear. The Spitfire M anchor began to fall below the performance of the FW-190 at several altitude bands, and the British accelerated the introduction of improved variants. The intact capture of an FW-190A3 in 1942, after Armin Faber mistakenly landed in Wales, enabled exhaustive testing. The results confirmed clear advantages in low and medium altitude speed, superior roll rate, and a more powerful weapons platform. The Allied response focused on engine and performance upgrades for the Spitfire, culminating in models capable of regaining parity in key scenarios. At the same time, the FW-190 demonstrated a versatility the Bf-109 could not match as easily. On both the eastern and western fronts, the F and G variants adapted to ground attack roles, carrying bombs, rockets, and cannon pods, and operating against motorized columns, trains, and defensive positions. Its structure and landing gear allowed operations from rougher airstrips, facilitating deployments closer to the front. By 1944, however, the pressure shifted again. Allied escort coverage and numerical superiority forced increasingly risky tactics, including formations designed to break through bomber boxes at close range, with heavy losses once Mustangs arrived on the scene. The Dora D variant, fitted with a Jumo 213 inline engine, sought to recover high-altitude performance and top speed, approaching 700 km per hour, but it arrived when the Luftwaffe was already suffering from fuel shortages and a deficit of trained pilots. In January 1945, Operation Bodenplatte, the German New Year's air offensive against Allied airfields, revealed that contradiction. It succeeded in destroying numerous aircraft on the ground, but at the cost of irreplaceable losses among leaders and veterans. With the Focke-Wulf 190, Germany had shown it could build a frontline fighter capable of forcing the enemy to adapt, but the problem no longer lay solely in design. It lay in the ability to sustain it in combat. The same dilemma, scaled up to the industrial level, defines the next major Allied technological leap, the bomber that changed the parameters of aerial warfare in the Pacific, the B-29 Superfortress. The most dangerous American bomber of the war, B-29 Superfortress. The war in the Pacific presented a distance problem that did not exist in Europe. Between US bases and Japan's main islands lay thousands of kilometers of open ocean, and the bombers available at the start of the conflict could not sustain regular attacks on Japanese strategic targets. The answer was the B-29 Superfortress, a program launched before the attack on Pearl Harbor that became the most complex and expensive bomber produced during the war. Its value did not rest solely on payload and range, but on integrating technologies that enabled high-altitude operations for long hours over routes without ground references. The B-29 incorporated a pressurized cabin to reduce crew fatigue and allow operations above 9,000 meters, as well as remotely controlled defensive turrets with centralized computation, designed to improve accuracy and reduce crew exposure. Its power plant consisted of 4 Wright R3350 radial engines, powerful but troublesome, prone to overheating and fires. a limitation that required constant modifications. With a large internal bomb bay, it could carry several tons of ordnance and maintain operational ranges that made it viable to strike Japan from forward positions. The first operations began in 1944 under Operation Matterhorn, the codename for the initial US strategic bombing campaign against Japan. It relied on airfields in China, an arrangement that was technically feasible but logistically fragile. Fuel, bombs, and spare parts had to be transported from India over air routes crossing the Himalayas at enormous cost in time, effort, and resources. Initial results were limited and operational costs high, with accidents and mechanical failures that sometimes exceeded losses due to enemy action. The situation changed after the capture of Saipan, Tinian, and Guam, which offered adequate infrastructure and sustainable striking distance to the Japanese archipelago. From there, regular missions against Tokyo began. High-altitude bombing encountered an unexpected obstacle. Jet stream winds diverted bombs and reduced accuracy. In 1945, command passed to Curtis LeMay, who redirected the campaign toward low-altitude night incendiary attacks aimed at crippling Japan's dispersed military production embedded within urban areas. On March 9th and 10th, 1945, a major raid over Tokyo caused widespread fire destruction and resulted in massive, quantifiable casualties, followed by similar attacks against other cities. In August 1945, the B-29 served as the delivery platform for the 2 nuclear weapons dropped on Hiroshima and Nagasaki. Its operational trajectory combined innovation, persistent technical failures, and a decisive final ability to bring the air war directly to Japan's industrial and administrative core. In Europe, however, years earlier, Germany had imposed an almost opposite model of aerial attack, not based on high altitude and long distances, but on steep diving and immediate coordination with ground forces. That concept became associated with a specific aircraft, the Junkers Ju-87 Stuka, the German dive bomber that became one of the most recognizable symbols of the Blitzkrieg, Germany's lightning war doctrine in the early stages of the conflict. Junkers Ju-87 Stuka, the psychological weapon of the Blitzkrieg. Dive bombing existed as a concept before the 1930s, but it only became systematic once aircraft structures were strong enough to withstand the forces generated during pullout. The Junkers Ju-87 was designed from the outset to strike pinpoint targets, coordinated by radio with ground units, and to turn air power into a rapid substitute for artillery. Its silhouette was functional, fixed, spatted landing gear, an inverted gull wing that facilitated the landing gear installation and kept the propeller high, and a configuration that prioritized stability in the dive over maximum speed. Its operational key lay in the attack method. The pilot initiated the dive from several thousand meters using dive brakes to limit speed and maintain control, released the bomb at low altitude, and recovered with a system that helped pull the aircraft out even under high G loads. This process allowed bombs to be placed with a precision difficult to match by horizontal bombers of the era. It carried a main bomb under the fuselage and smaller charges under the wings, with limited defensive armament and a speed that left it exposed if operating without cover. Under favorable conditions, its effect was immediate: destruction of bridges, artillery positions, troop concentrations, and moving columns, with a direct tactical impact on ground maneuvers. Beginning in 1939 in Poland, it was used to strike airfields, isolate troop movements, and clear the way for armored columns. In 1940, during the campaign in France and the Netherlands, it fit into a repeated sequence: reconnaissance and initial contact, radio designation of an obstacle, dive attack, and resumption of the advance. In Norway and later in maritime theaters, the Stuka was also employed against ships, using the dive profile to visually correct the point of impact on a moving target. This capability cemented its reputation as a precision tool during Germany's early successes. Its vulnerability was exposed during the Battle of Britain. Faced with radar detection, fighter patrols, and organized anti-aircraft defenses, it proved too slow to survive without air superiority. After concentrated losses in August, it was withdrawn from that front. On the Eastern Front, beginning in 1941, it again operated with greater freedom during the initial phase, and adapted to anti-tank roles in cannon-armed variants, striking the less protected areas of Soviet armor. As enemy air defenses improved, its survival margin steadily shrank. The Stuka left a clear lesson. The precision of dive bombing was valuable, but depended on a controlled sky. That need to operate under direct fire and to return repeatedly to the front line foreshadowed the logic of the next aircraft, an American fighter designed to withstand damage and convert firepower into destruction at low altitude, the P-47 Thunderbolt. P-47 Thunderbolt, the hammer of the Allied ground attack. When the P-47 arrived in Europe in late 1942, its size and weight set it apart from the classic image of the lightweight fighter. It was the largest single-engine aircraft mass-produced by the United States, powered by a Pratt & Whitney R2800 radial engine and a turbo-supercharger system installed in the fuselage, which provided stable power at high altitude. Its standard armament, 8.50 caliber Browning machine guns, offered a density of fire difficult to match, and its structure was designed to absorb hits that would destroy lighter aircraft. These qualities defined its trajectory, first escort and air combat, and increasingly, ground attack. In 1943, it operated as a bomber escort, especially with the United States 8th Air Force in Europe. With external fuel tanks, it extended its range, but it still fell short of the Mustang, which took over deep escort missions in 1944. That shift freed the P-47 for intensive use with the 9th Air Force. The aircraft could carry bombs and rockets in addition to its machine guns, and its ruggedness made it suitable for low-altitude missions where light anti-aircraft fire was constant. From the preparations for the Normandy landings onward, P-47 systematically attacked transportation infrastructure, railways, stations, bridges, convoys, and depots. The logic was operational and measurable: break German mobility, force detours, slow reinforcements, and degrade fuel and ammunition supply. Once the front opened in France, the pattern repeated daily. Pilots struck locomotives and trucks from low altitude, followed roads and junctions, and used rockets and bombs against fortified positions and vehicle concentrations. The visible effect was a drastic reduction in daytime movement, more traffic at night, greater dispersion, and increased reliance on secondary routes. In the Ardennes, during the German counteroffensive of December 1944, the P-47 became relevant again once the weather improved and tactical aviation regained freedom of action. Its contribution was not a single decisive strike, but a matter of repetition and volume, cutting fuel supplies, destroying transport, and forcing armored units to operate without logistical continuity. The P-47 was neither the most elegant nor the longest-range fighter, but its combination of power, payload, and survivability made it a constant tool of attrition. That same principle of endure and sustain defines the next Allied icon, one that kept a nation in the war when air superiority was a condition for survival: the Supermarine Spitfire. The Shield of Britain, Supermarine Spitfire. In 1938, the first Spitfires reached operational RAF squadrons, and in less than 2 years, they went from a technical novelty to a critical component of national defense. The design addressed a specific requirement: an interceptor capable of rapidly reaching incoming bombers and engaging escort fighters in British airspace. Its elliptical wing was not an aesthetic feature, but an aerodynamic solution to reduce induced drag and maintain high speeds with strong maneuverability. With an all-metal structure, enclosed cockpit, and retractable landing gear, the Spitfire represented a leap over the previous generation. Powered by the Rolls-Royce Merlin, it entered combat with initial configurations of 8.303 caliber machine guns designed to concentrate fire during short firing passes. The decisive test came between July and October 1940. The Luftwaffe aimed to neutralize Fighter Command, the body responsible for Britain's air defense, to pave the way for an invasion that ultimately never took place. In numerical terms, Hurricanes bore much of the burden, but the Spitfire played a specific role, engaging the Bf-109 and reducing pressure on the fighters attacking bombers. At medium and high altitudes, the Spitfire could sustain turning engagements with an advantage, while the Bf-109 tended to impose climbs and dives to break contact. The difference was not determined solely by aircraft-to-aircraft performance, but by the integrated system. The chain-home network, Britain's coastal radar, detected incoming formations, and ground control organized interceptions with precise timing, avoiding unnecessary patrols and conserving engine hours and fuel. The Spitfire also evolved rapidly. The appearance of the FW190 in 1941 made it clear that a successful model could be surpassed within months. The British response was to accelerate new variants with more powerful Merlin engines and improved supercharging, a process culminating in the Mark IX from 1942 onward, which restored operational parity. Armament was also revised. Experience against bombers revealed the limitations of the .303 caliber, and mixed configurations with Hispano 20mm cannons were adopted. This flexibility allowed the aircraft to perform interception, escort, limited ground attack, and reconnaissance missions, taking full advantage of its high-altitude performance. From 1944 onward, the Spitfire no longer defended only British skies. It operated from forward bases on the continent. In later Griffon engine variants, the Spitfire gained speed and climb rate, and it was even employed against the V-1 flying bombs. More than 20,000 units were produced, and its longevity was sustained because the design accepted new engines, wings, and armament without losing stability or control. This technical and operational achievement had a practical reality. Britain had survived when air superiority was a condition for survival. With the skies secured, Allied air warfare could move into a phase of deep offensive operations. The next protagonist in that transition was a bomber capable of penetrating deep into German territory on daylight missions and returning despite damage that would seem incompatible with flight: the B-17 Flying Fortress. B-17 Flying Fortress, the fortress that bombed the heart of the Reich. In August 1942, the first American B-17s flew missions over occupied Europe, but the real test came in 1943, when the daylight offensive reached Germany and losses rose to levels that called the entire campaign into question. The problem was structural. Daylight bombing required concentration of aircraft to sustain defensive fire, and that concentration attracted fighters and increasingly coordinated anti-aircraft artillery. In missions such as Regensburg and Schweinfurt, in August and October 1943, dozens of bombers were shot down in a single sortie. Each aircraft carried a crew of 10 men. At that scale, strategic bombing was not just an industrial plan, it was an equation of replacing both material and personnel. The B-17 had been conceived in the 1930s as a bet on range, altitude, and survivability. With 4 engines, it could sustain high-altitude flight while carrying a significant payload over long distances. Its evolution culminated in versions equipped with numerous .50 caliber machine guns arranged for almost complete coverage, including a front turret to counter head-on attacks, a tactic developed by German pilots to minimize exposure time to gunners. US doctrine aimed for daylight precision bombing of industrial targets, and to execute it, B-17s flew in staggered boxes that overlapped fields of fire, creating a defensive volume intended to deter interceptions. Practice revealed limitations. German fighters attacked in coordination, concentrating passes and breaking off quickly. Heavy anti-aircraft artillery, directed by radar and control centers, forced evasive maneuvers and dispersal. But the decisive factor in 1943 was the escort gap. Allied fighters could not reach deep targets, leaving B-17s exposed for hours. The campaign slowed until escorts capable of accompanying them to the heart of Germany appeared. With the massive deployment of the P-51 in 1944, relative losses fell, and the Luftwaffe was forced to fight under unfavorable conditions, losing veteran pilots and aircraft in the process. From then on, the B-17 became part of a sustained offensive against synthetic fuels, rail transport, and industrial centers, while supporting ground operations with saturation bombing during specific phases. More than 12,000 units were built, and the aircraft gained a reputation for structural resilience, evident in returns with severe battle damage. However, its impact cannot be separated from the complete system. Escort fighters, navigation, photographic intelligence, mass production, and a doctrine that accepted losses to maintain constant pressure. That same lesson in air supremacy connects to the next theater, where an enemy fighter initially dominated due to its range and maneuverability. Mitsubishi A6M Zero, the absolute ruler of the early Pacific. In 1941, the Japanese Naval Air Force entered the war with a carrier-based fighter optimized for a very specific type of campaign: long distances, combat over open sea, and air superiority achieved through maneuverability and range. The Mitsubishi A6M Zero was designed to operate from aircraft carriers with exceptional endurance and to dominate in close-range combat against heavier aircraft. Its early strategic effect was not explained solely by the aircraft itself, but by the combination of a lightweight platform, highly trained pilots, and a doctrine aimed at destroying the enemy in the air before it could reorganize. The Zero originated from a 1937 Imperial Japanese Navy requirement calling for high speed, cannon armament, escort capability, and range sufficient to operate hundreds of kilometers from the fleet. To achieve this, Mitsubishi and the team led by Japanese engineer Jiro Horikoshi minimized weight. Light alloys were used, and elements considered essential in other countries were removed: significant pilot armor and self-sealing fuel tanks. The result was a highly maneuverable aircraft with relatively low fuel consumption and a range superior to most contemporary fighters. In early variants, it combined two 20mm cannons with machine guns, sufficient to shoot down fighters and damage bombers in short attack passes. The Zero saw combat before 1941 in operations over China, where it gained a significant initial advantage against less equipped forces and inferior platforms. During Japan's expansion in late 1941 and early 1942, it supported attacks across a broad arc including the Philippines, Malaya, and the Dutch East Indies, providing cover for bombers and naval forces. During this period, many available Allied fighters, such as the F-2A Buffalo or early P-40 models under certain conditions, could not match its sustained turning ability or operational range. In low-speed engagements, the Zero dictated the terms of combat and punished mistakes. Its weaknesses, however, were structural and predictable. The lack of armor made heavy-caliber hits lethal, and the non-self-sealing fuel tanks increased the risk of fire. Additionally, at high speeds, control responsiveness degraded and the aircraft lost part of its advantage, especially if the opponent avoided close-range combat. From 1942 onward, Allied pilots began applying energy tactics, diving attacks, high-speed passes, and immediate disengagement, avoiding turning fights. Over time, the loss of experienced Japanese pilots and the introduction of US fighters designed to absorb damage while maintaining speed reduced the Zero's margin of superiority. In 1943 and 1944, fighters such as the F6F Hellcat, with greater power, improved protection, and much more lethal concentrated fire, fully shifted the balance in the Pacific. The Zero remained in service until the end of the war due to the lack of sufficient replacements, but its role changed. From air combat dominator, it became a clearly outclassed platform. This shift sets the stage for the next chapter. The US naval fighter that achieved the majority of carrier-based air-to-air victories and became the principal instrument in dismantling Japanese air power over the open ocean. F6F Hellcat, the Zero's executioner. The F6F Hellcat emerged in 1942 as a direct response to the characteristics of the Japanese A6M Zero. Grumman engineers had studied operational reports from the first Pacific engagements, but the arrival of an almost intact Zero from Akutan allowed precise evaluation of its light structure, lack of armor, and loss of control at high speeds. This confirmed the need for a fighter with advantages in power, structural resilience, and armament. The Pratt & Whitney R2800 engine, delivering over 2,000 horsepower, placed the Hellcat in a performance range where it could initiate and disengage from combat at will, avoiding maneuvers where the Zero still held an edge. The design prioritized protection, self-sealing fuel tanks, pilot armor, and a fuselage capable of sustaining hits without compromising integrity. Armed with 6.50 caliber machine guns, the Hellcat concentrated enough firepower to penetrate light structures within seconds. It entered operational service in 1943 aboard Essex-class aircraft carriers and was rapidly adopted as the primary US carrier-based fighter due to its ease of maintenance, stability as a firing platform, and damage tolerance. Its effectiveness was proven in 1944 during the Battle of the Philippine Sea. There, the already weakened Japanese air forces faced pilots with more extensive training and aircraft with superior tactical margins. Hellcat formations intercepted Japanese waves with results that clearly demonstrated the shift in balance. The combination of speed, power, and stability allowed US pilots to execute controlled attacks and return to the carrier deck even after sustaining multiple hits. In the subsequent Battle of the Philippine Sea, the Hellcat demonstrated its capabilities in mixed scenarios, from massive interceptions to fleet support. The skill accumulated by pilots such as David McCampbell, who achieved over 30 victories, reflected not only individual ability, but also the coherence of the training system and the aircraft platform itself. By late 1944, the Japanese Naval Air Force could no longer replace crews or aircraft quickly enough, while the United States increased production and rotation without interruption. The total number of confirmed Hellcat kills exceeded 5,000, with a highly favorable ratio in air-to-air combat. Its production, over 12,000 units, ensured constant availability for carrier operations across the Pacific. This dominance marked the end of the Zero as a decisive factor. While the Pacific tilted toward carrier-based air power, a very different front was being shaped by an armored aircraft designed for low-altitude combat. IL-2 Sturmovik, Stalin's flying tank. The IL-2 Sturmovik was the result of an unusual approach in aircraft design, building a ground attack plane with structural armor integrated into the airframe. The project, initiated in 1938 in the bureau of Sergei Ilyushin, a Soviet aircraft designer, aimed to provide sufficient frontal protection to operate at low altitude against small arms and machine guns. The forward section, from the engine to the cockpit, formed an armored unit that safeguarded the pilot and vital components. The Mikulin AM-38 engine was optimized for low-altitude performance, suitable for direct support missions for the Red Army. When the German invasion began in June 1941, the number of available IL-2s was limited and training insufficient. Early units suffered significant losses against enemy fighters, especially in the rear, where the initial single-seat versions lacked defensive armament. After the first months, production accelerated, and two-seat variants with a rear gunner were introduced, improving survivability against attacks from above and behind. The relocation of factories eastward allowed production to continue under extreme pressure, making the IL-2 one of the most produced military aircraft in history. In 1942 and 1943, the Sturmovik became an essential tool at Stalingrad and Kursk. Its attacks targeted mechanized columns, fortified positions, and logistical concentrations. Armed with 23mm cannons, bombs, or unguided rockets, it could neutralize vehicles and artillery with relative precision from low altitude. Although Soviet figures tended to overestimate damage, the tactical effect was tangible. It forced the enemy to disperse and complicated daytime movements. Its ability to absorb damage, often documented in returns with extensive punctures in wings and fuselage, created among German troops the perception of an exceptionally resilient aircraft. Production exceeded 30,000 units, allowing its use in large numbers during each phase of Soviet offensives from 1943 onward. Its role remained consistent: close support, attack on armored vehicles, and disruption of enemy forces in the immediate rear. It was a specialized aircraft, not a multi-role one, but it fulfilled the purpose for which it was designed. As the war moved into Central Europe, the IL-2 accompanied ground forces in their sustained advance. This close interaction between tactical aviation and land maneuver contrasted sharply with another category of German aircraft that had represented the Reich's initial offensive power: medium strategic bombers. Heinkel He 111-1, the Blitz bomber. He 111 was conceived in the mid-1930s under the guise of a civilian transport aircraft, an attempt to circumvent the restrictions of the Treaty of Versailles while Germany rebuilt its air capabilities. Its early military versions evolved from this streamlined fuselage into a twin-engine bomber with internal bomb storage and a reduced crew. The model developed rapidly, and by 1937 it saw combat in the Spanish Civil War with the Condor Legion, the German air unit deployed to Spain, demonstrating sufficient speed to evade Republican fighters and the capacity to carry bombs on support and infrastructure targeting missions. By 1939, the He 111 had become a cornerstone of the Luftwaffe in the medium bomber category. Its P and H variants introduced a glazed nose, providing better visibility for the bombardier and becoming its most recognizable visual feature. Equipped with Daimler-Benz or Junkers engines depending on the version, it could carry moderate payloads over distances suitable for campaigns in Europe. Defensive armament consisted of machine guns in the nose, dorsal and ventral positions, adequate against light threats but insufficient against modern fighters. The He 111 participated in campaigns in Poland, Norway, the Netherlands and France, operating in environments where aerial opposition was limited or scattered. The situation changed during the Battle of Britain, when the bomber faced a well-organized RAF, supported by radar and fighters capable of rapid interception. Its maximum speed and defensive armament revealed clear limitations against Hurricanes and Spitfires. Losses increased significantly during daytime missions, prompting a shift toward nighttime bombing during the Blitz of 1940–41. In this role, it benefited from radio navigation systems that improved relative accuracy in low visibility conditions. In subsequent years, the He 111 was adapted for multiple roles: naval torpedo bomber, transport, and glider tug. It participated in operations in the Mediterranean, the Eastern Front, and logistical support campaigns. However, the advance of Allied fighters and improved anti-aircraft defenses reduced its operational margin. Production, nearing 7,000 units, gradually declined as Germany prioritized fighters to defend its airspace against increasing Allied raids. Although surpassed by more modern aircraft like the Ju-88, the He 111 remained an early symbol of German offensive power. Its use during the Blitz left a lasting impression on the British public and in the iconography of aerial warfare. From 1942 onward, the Luftwaffe sought to strengthen defensive capabilities with multi-role models that could replace the He 11-1 in speed and adaptability, including the Bf-110 and later versatile aircraft, such as the de Havilland Mosquito, the protagonist of the next chapter. Messerschmitt BF-110, the destroyer destroyed. The Messerschmitt BF 110 first flew in 1936 as a twin-engine heavy fighter designed for a specific role: long-range escort and bomber destruction. The Luftwaffe integrated it into the Zerstörer concept, the German destroyer fighter category, an aircraft intended to combine autonomy, sustained speed, and frontal firepower to assert superiority against less modern air forces. The initial operational variants mounted Daimler-Benz engines and a battery of cannons and machine guns concentrated in the nose, complemented by a rear gunner. In scenarios with limited or disorganized opposition, the model fulfilled its intended purpose. In 1939, during the campaign in Poland, the Bf 110 operated against an air force with inferior equipment and deployment, performing favorably. During the 1940 offensive in Western Europe, it remained useful in escort, patrol and attack roles, but structural limitations began to emerge. Against modern single-engine fighters, the Bf 110 relied on maintaining energy and avoiding close combat. Its size and the extra fuel weight for long-range missions penalized acceleration and turning, and any loss of speed made it vulnerable to attacks from above and behind. The Battle of Britain exposed these limitations unequivocally. The Bf 110 had to accompany bombers at speeds that favored British interceptors and operated over territory where fighter command could concentrate forces guided by radar. Losses increased in August 1940, and the need for the Bf 110 to be escorted by Bf 19s highlighted the collapse of the concept as a daytime superiority fighter in this theatre. From that point on, the type was progressively withdrawn from the daytime escort role in the West, although it continued to be used in secondary roles and in areas with lighter opposition. On the Eastern Front from 1941, the Bf-110 regained some effectiveness when facing obsolete Soviet aircraft and initially disorganized forces. Even so, as opposition improved, losses rose. The solution was to reassign it to an environment where its characteristics were functional: night interception. The Bf-110 was adapted as a night fighter with the German Liechtenstein airborne radar, extended patrol capability, and a stable platform for approach and firing against heavy bombers. In this role, its frontal firepower translated into kills against Halifax and Lancaster bombers, and its range allowed it to maintain patrols within the German defensive system. Thus, the Bf-110 transitioned from a daytime destroyer to a specialized night interceptor. Its history reflects a recurring pattern in the Luftwaffe, an aircraft useful in early scenarios, outclassed in daytime combat by enemy evolution, and converted into a key component of nocturnal warfare. This contrast between daytime vulnerability and nighttime effectiveness sets the stage for the next chapter, focused on a British aircraft that reversed the logic. It abandoned heavy defense to survive through speed and profile. De Havilland Mosquito, the aerodynamic design that broke the rules. The de Havilland Mosquito originated from a proposal that went against the orthodoxy of 1939. A fast aircraft, built largely of wood, without defensive turrets, with absolute priority on speed and operational range. The idea leveraged two real conditions of the British wartime economy: pressure on aluminum and the existence of an industry capable of precision woodworking, including civilian workshops. Its structure was based on laminated and bonded sections, with a clean aerodynamic design and two Rolls-Royce Merlin engines that provided performance capable of outperforming many fighters of the era under certain altitudes and configurations. The prototype flew in late 1940, and production was consolidated in 1941 to 42. The Mosquito was first used in photographic reconnaissance, where the combination of speed, altitude and range allowed it to penetrate defenses and return with intelligence material without requiring escort. This role became an operational multiplier. Photographs of facilities, ports and railway nodes fed bombing planning and damage assessment. From 1942 onward, the Mosquito undertook fast day and night bombing missions, striking pinpoint targets with moderate payloads but relative precision and lower loss rates than heavy bombers. Its main value was versatility. The same airframe supported variants as a light bomber, night fighter, night operational interceptor, fighter bomber, pathfinder target marker, and maritime attack aircraft. Fighter variants integrated Hispano cannons and machine guns, making it an effective interceptor against bombers and, in some cases, against V-1 flying bombs. As a pathfinder, it marked targets with flares and indicator bombs to guide Lancasters and Halifaxes, increasing the accuracy of night bombing. The Mosquito was also employed in low-altitude operations against specific targets, where the attack profile demanded precise navigation and strict timing coordination. The operational logic was clear: strike a point at speed, minimize time within defensive coverage, and exit before interception was viable. Its maintenance benefited from distributed production and the relative availability of non-strategic materials compared to critical metals. Several thousand units were produced in the United Kingdom, Canada, and Australia, and it remained in service after 1945 due to its usefulness in reconnaissance and attack. The Mosquito demonstrated that an aircraft could substitute defensive armament with speed, planning, and execution. This efficiency, however, operated within a broader British strategy that relied on heavy night bombers capable of carrying payloads impossible for a twin-engine plane. The next chapter focuses on the primary of those bombers, the core of the RAF's night offensive. Avro Lancaster, the RAF's night hammer. The Avro Lancaster became the primary heavy bomber of the British Bomber Command from 1942, as the RAF consolidated its strategy of night raids over Germany. Its success relied on a practical feature: a superior payload capacity compared to other contemporary British models, combined with a range that allowed operations against industrial targets in the Ruhr, Hamburg, Berlin, and later the heart of Germany. Powered by 4 Rolls-Royce Merlin engines, The Lancaster combined operational altitude, flight stability, and a bomb bay capable of carrying large ordnance loads in configurations that other bombers could not accommodate. The night campaign depended on navigation, target marking, and volume. The Lancaster integrated into this system with techniques that included decoys, limited electronic warfare, variable routes, and the work of Pathfinder units, squadrons specialized in target marking, often equipped with Mosquito aircraft. German defenses responded with radar, anti-aircraft artillery, and night fighters, creating an interception battle where survival depended on formation discipline, altitude, weather, and countermeasures. Despite these challenges, the Lancaster maintained a steady operational tempo, allowing repeated strikes on railway hubs, factories, refineries, and urban centers linked to production and logistics. Its versatility was evident in special missions. In 1943, Operation Chastise, the raid on the Ruhr dams, employed modified Lancasters to deploy bouncing bombs with concrete results, structural damage and temporary disruption of industrial water and power supplies. Later, the Lancaster served as a platform for the tallboy bombs, heavy penetrators, and the Grand Slam, seismic bombs of extreme penetration, designed to destroy reinforced structures, viaducts, and bunkers. These payloads required specific modifications and specialized training, expanding the range of achievable targets. In 1944–45, in addition to strategic bombing, the Lancaster participated in support of ground campaigns, including logistical preparation ahead of Allied operations. The operational conclusion was clear. The Lancaster provided the RAF with a tool to maintain sustained nocturnal pressure, with a heavy payload integrating into an intelligence, navigation, and target marking system that evolved throughout the war. With the Lancaster, night air warfare reached an industrial scale. Yet that scale coexisted with another reality: the continuous adaptation of German night fighters, the evolution of radar and countermeasures, and the constant adjustment of routes and tactics. This cycle of action and reaction set the stage for the Reich's defensive systems, which evolved in parallel to face an offensive that no longer depended on a single aircraft, but on a complete integrated network.